Okay, we've talked a little bit about kinetics and about rate laws, and now what you're going to do is you are going to be able to determine the order of a reaction, and we do that by method of initial rates. So if you see these initials, that stands for method of initial rates. So it's just a process where we can go through and figure out the orders of reaction. So you have all of these notes. These are really meant for you to just be able to read through and work on them by yourselves. But I will kind of sum some things up. Remember that when you have a reaction like this, it is a reaction. We're looking at that reaction for that slow step because that slow step is that rate determining step. It's going to dictate how fast that reaction progresses. And then when you write down a rate, your rate is going to be equal to a constant, which we call K, and we multiply that times the concentration of A raised to the power of its coefficient times the concentration of B raised to the power of its coefficient. So in theory, I guess we could have these be X's and Y's is what we're looking at there. But that's what we're going to be thinking about. And this is just a quick little something about, you don't have this in your notes, but just goes through telling you how to go about determining the method of initial rates. And you're going to basically find two trials because you've got these experimental trials. And you're going to find two trials where only one reactant changes concentration. So you'll be able to compare those and determine what that exponent is. So once you get to the point where you get an exponent, and I'm looking down here now, but if it says 2 to the x equals 1, this is just a little math reminder for you. That would mean that x equals 0. And then 2 to the x equals 2, we know that that would be x equals 1. 2 to the x equals 4, that's x equals 2. So now with all of that in mind, let's go ahead and do our couple example problems that we have there. And the first one that we have, we see that we have this reaction M plus N yields P plus Q. So I know that my rate is going to be equal to a constant times the concentration of my reactants, so M and N, raised to the power of their coefficients. So it's going to be an X and then a Y. So that's what my rate law is going to look like. So now what I need to do is I need to figure out which two experiments have only one of those concentrations equal. So maybe over here I'm going to write EXP for experiment 1, 2, and 3. So the first thing I might look at, I look at experiments 2 and 1, and I notice that N happens to be the same. So in that case, I can determine the order of reaction for M. So in this case, and I'll even make the notes during this to show that we're looking at experiments 1 and 2, but it sure makes my math a lot easier to put the larger number on top and the smaller number on the bottom. And when I talk about larger number and smaller number, I'm talking about my concentrations and my rates. So I look and I see for experiment number 2, 5 times 10 to the negative third is bigger than 2.5 times 10 to the negative third, as is 0.02 is bigger than 0.01. So it makes more sense to put 2 on top of 1. So when I set this up, I'm going to say that my rate, which is going to be, remember I'm following this, so my rate is going to be 5 times 10 to the negative third divided by 2.5 times 10 to the negative third. And that's going to be equal to a constant, K, times the concentration of M. So M is going to be 0.02 raised to the power of X times the concentration of N, which is 0.01, raised to the concentration of Y. And I have to do that for experiment 1 as well, so this is K. And here we have 0.01 raised to the power of X and 0.01 raised to the power of Y. So immediately, the reason I set this up was so that I could get my y's out of the way. I intentionally wanted those to cancel so that I only have to deal with one variable at a time. And then, of course, my k's cancel as well. So when I plug this in the calculator, I end up getting 2 equals 2 raised to the x So that's going to be x equals 1. I have just done half the problem, so now I can go ahead and I can try and solve my y as well. So I've just determined that, let me see here, these guys were the same, I got them to cancel, so now I can look over here and see that these are the same as well. I want these to cancel. So the way I'm going to set this one up is I'm going to say experiment 3 over 2, and we're going to set that up as 4.5 times 10 to the negative 2 divided by 5.0 times 10 to the negative 3, which I'm not even going to bother writing down my k's or my x's because I purposely got those to cancel. So I'm just going to write down my y's, and that's going to be 0.03 raised to the y divided by 0.01 raised to the y. So in this case we get 9 equals 3 raised to the y, so y equals 2. So now with this information we can go ahead and we can calculate, we can plug it in and actually get a rate law. And I think I need to write smaller. Rate equals, it's going to be K times the concentration of M raised to the first power times the concentration of N raised to the second power. So now you have your rate law. We can go ahead and actually plug in some values also, because the question says not only what is the rate law for the reaction, but what is the value of the rate constant. So that rate constant is K that we're looking for. And in this case, I'm going to find myself some room over here, that we are going to go ahead and just choose your first experiment. That's pretty much the protocol for how this is done. So I can go ahead and say, I'm sorry, this is going to be sloppy, 2.5 times 10 to the negative third is equal to K times 0.01 raised to the first, and then 0.01 raised to the second. So when you go through and solve this, you end up getting, I'm going to let you guys kind of throw this into your calculator, but you end up getting K equals 2,500. So now our ultimate answer, when we throw this all in, we get rate equals 2,500 times M raised to the first times N raised to the second. That is your rate law. Okay, second one. In this situation, really the same type of question. We've got all of this data that's been determined experimentally, and we're told the reaction. We want to determine the rate law and the rate constant for the reaction. So again, you're going to go through here, and you're going to say that experiment, here's 1, 2, and 3. If I work with experiments 1 and 3, I can get my y's to cancel out. So I think I'll do that, and I want 1 to be on top because that's larger for my concentrations and my rate. So 1 divided by 3, which gives me rates of 227.2 divided by 28.4, and that's going to be equal to 0.004 raised to the x divided by 0.002 raised to the x. So little math, I'm sure you all are plugging this into your calculator right now, and you get 8 equals 2 raised to the x equals 3. And then for our second one, in order to get two things to be constant, I look at these. Now I can solve for, remember this is my x, this is my y. So now I can say that experiment 2 divided by 3 would be the way to go. And I get 255.6 divided by 28.4 is going to be equal to 0.06 raised to the y divided by 0.002 raised to the y. And we get, oops, I'm jumping the gun here. We get 9 equals 3 to the y. So y equals 2. So now we know the orders of both of those, and we can say that the rate equals K times NO is our first one, that's for X, and that's going to be raised to the third power. And oxygen is raised to the second power. So with respect to NO, it's third power, or third order, and with respect to oxygen, it's second order. So then we can go ahead and plug in and find the value of K. So we get 227, remember I'm just choosing this first experiment. 227.2 equals K times 0.004, and I'm going to raise that to the third power. And then we take our second one here, which is 0.002, and we raise that to the second power. Then we just go ahead and do our math, and we end up getting K equals 8.875 times 10 to the 14th. So now that you have that, you can go ahead and plug that into your rate law, and you get rate equals 8.88, let's call it that, times 10 to the 14th, and we will say that's times the concentration of NO raised to, this is going to be raised to the third, and times the concentration of O2 raised to the second. That's all there is to it. Now get to work.